Thank you for joining us for today's webinar. My name is Bill Kozad. I'm the Digital Marketing Manager at Yokogawa Corporation of America. Today, we are presenting Fundamentals of Fabulous Flow Measurement, presented by Paul Warburton and Craig Longcor. Also joining us for our Q&A session at the end will be Chris Koslow, who leads Yokogawa's Flow Product Marketing. Now, without further ado, we're going to turn our time over to Paul Warburton and Craig Longcor. Paul has 28 years of industry experience, with the last 24 years working at Yokogawa. He is currently the Southeast Regional Field Application Sales Specialist. Previously held positions include Flow Meter Product Management and Technical Support Team Leader for Field Instruments. Paul has a BS in Electrical Engineering Technology from the State University of New York. Craig has 30-plus years experience in sales, service, and the application of process control instrumentation and analyzers. He has been with Techstar for the past 16 years. Craig has held positions in product sales, sales management, and field service management. He has a BS in Engineering Technology from West Texas State University. Outside of work, Craig enjoys fishing and sailing. Take it away, Paul and Craig.
Thanks, Bill.
Thank you. Good morning, everybody. Hope everyone's doing well and safe. So today we're going to spend some time flow technology. We're going to review the theory behind some of these technologies, go through some applications, talk about the different technologies when selecting a meter and which technology is best suited for your flow measurement, and then also get in some of the installation best practices. So the technologies we're going to be discussing today are magnetic flow meters, vortex meters, Coriolis. We'll touch on some of the different type of primary elements with differential pressure measurement, ultrasonic meters, and then lastly, the variable area meters. So first we'll start off with the magnetic flow meters. So how a mag meter works is it's a line tube, typically a PFA or PTFE type liner. And if you look at the illustration in the middle, you see two coils, one at the 12 o'clock position and one at the 6 o'clock position. And then you also see two measuring electrodes, and they are at the 9 and 3 o'clock positions. So a mag meter is based off of Faraday's law, where if you have a magnetic field and you break through that magnetic field with a conductive force, the resultant output is going to be a voltage potential. So in the mag meter, you have the two coils, and we energize those coils, creating a magnetic field within the meter. And as your conductive process breaks through that magnetic field, the electrodes are picking up that electromotive force, and that voltage is directly proportional to your flow rate. So there's different types of excitation methods. When mag meters first came out, the first type of excitation method was AC, and that was basically plugging a meter into your outlet in a wall. That was very good because it had a very good response time of 60 hertz, because your power in your outlet is 120 volts, 60 hertz. So it had a very fast response time, which made it very good for slurry applications. The bad part of the AC technology was that the accuracy wasn't very good, because it was a percent of span device, and it also used up a lot of power. And also the zero stability was not very good. So years later, customers, end users, and manufacturers got together and started discussing the different technologies of how we can improve on the AC excitation, and along came pulse DC excitation. And you can see here, the pulse DC excitation gives you a very good zero stability, very low power consumption because it's a DC type circuit. Accuracy greatly improved from a percent of span device to a percent of flow reading. But because the pulse DC is typically in the 6 to 10 hertz range, it decreased your response time, and it made it not so good for slurry type applications. Several years later, along came another technology called dual frequency excitation. And dual frequency excitation basically brings the best of both worlds between AC and pulse DC. So the dual frequency is two simultaneously pulsed DC signals, one at around 6.5 hertz and the other one at 65 hertz. So they're superimposed on one another and continuously sampling at both a high frequency and a low frequency. So what this does, it pretty much gives you the best of both worlds and gives you a very good zero stability, very good low power consumption, very high accuracy, and the high pulse signal gives us a very fast response time, making it very good for these slurry type applications. So if we hooked up an oscilloscope to a dual frequency device, this is the waveform you can see. And on the lower signal, you see the low frequency component. The middle one is your high frequency component. And then it superimposes one on the other. And in turn, you're left with this dual frequency type excitation. So mag meters are used in a wide variety of applications, but the one thing with a mag is that it has to be a liquid process and it must be a conductive fluid. Mag meters are known as line size meters because usually if you have a 4-inch line, you can stick a 4-inch meter in there. There are some exceptions to those rules. If you have a coating type application, say a latex paint, that's something, or a fatty type process, say in like a rendering plant, you may want to increase the velocity through the meter to help clean the electrodes. So you may want to reduce down, say, from that 4 to a 3-inch line. On the flip side, if you have a slurry type application or abrasive type application, you may want to decrease the velocity and go from, say, a 4 up to a 6. In those applications, in the abrasive applications, you typically want to keep your velocity in the 7 to 10 feet per second range. Mags have no moving parts. Like I said, it's a straight through tube. We have a wide variety of wetted materials for the electrodes and the grounding rings. You have stainless steel, Hastelloy C, platinum, titanium, tungsten carbide. So pretty much any application we can meet the materials required. And again, wide range from your general basic simple water type application all the way to a corrosive chemical or heavy slurry application. And as you can see, mags can be used in pretty much any place where something needs to be measured, from pulp and paper, food and beverage, mining, water, wastewater, chemical, steel, power, pretty much every industry out there, we have mag meters installed. Let's if we look at the pulp and paper, black liquor, pulp slurry, head box applications, these are all great applications for a mag meter. And you can see in any of the other industries, there's plenty of applications where we can use a magnetic fluid meter.
So you're right, all the mag meters really widely applied. Here we're showing a picture of the application where they're processing brine solutions to produce boric acid, sodium carbonate, sodium sulfate. For example, the boric acid is used to make monofilament fiberglass or textile fiberglass that gets used in things like anywhere from reinforced plastics, industrial piping, and even computer circuit boards. All of these components mentioned in this application are water-based, and they're a good fit for a lined or non-metallic flow meter, as the salts would have a lot less impact on the or a lot less negative impact on the electromagnetic flow meter. Here we're looking at some applications in the food and beverage industry where mag meters being used for soybean oil. Mag meters are a common selection in food and beverage industries because the internal geometry is easy to clean and it's available in sanitary versions which meet the requirements of the food processing industry, biotechnology, and pharmaceutical industries. You may also be interested to learn that Yokogawa has released an Ethernet IP communication protocol. And if anyone would like information on the Ethernet IP protocol, just let us know.
So the next technology we're going to talk about is the vortex flow meters. And the way a vortex meter works, similar in, based on a mathematician, von Karman effect. Like mag meters were based off Faraday's law. Vortex is the von Karman effect. And what the von Karman effect basically says that as you have a fluid coming down say a pipe and it's hitting a bluff body or shetter bar, the flow will shear off and vortices will be generated at an alternating rate. So basically what a vortex meter is doing is counting those vortices. So as the vortex formation increases, the output of the meter will increase, and as it decreases, the frequency decreases, the output decreases. So vortex is a linear device, and as flow increases, vortex creation also increases. So here's a good illustration of how a vortex meter works. So if we look at the flag in the upper left-hand corner, that would represent a light breeze. You can see the flag has very little movement. And in the flow terms, we would look at this from a Reynolds number of 0 to a 5,000 Reynolds number. So kind of a low flow type scenario. In the middle flag, you have a little bit stiffer breeze, and the flag has some movement, but it's not a consistent movement or ripple of that flag back and forth. And we would look at that as a little bit higher Reynolds number, somewhere in the 5 to 20,000 Reynolds number range. And then in the bottom flag, you can see the flag is rippling back and forth, and it's standing straight out because we have a strong breeze, strong wind, and our Reynolds number in that case is, say, greater than 20,000. So if we took that phenomenon, put that in the flow meter, in the illustrations to the right, in the upper right-hand corner, where you have low flow, the flow is coming down, hitting the shutter bar, and it's just sticking to the contour of the bar and continuing on down the line. In the middle illustration, flow is a little bit higher velocity, and we have some vortex formation, but it's not very repeatable or consistent. But then in the third illustration, where we have a higher velocity, greater than 20,000 Reynolds number, our vortices are going to be generated at an alternating rate and be very repeatable. So you can see in these illustrations here, if you have an application where you're trying to get down to a zero flow or a minimum flow, a vortex meter may not be best suited for your application. But if you have a relatively narrow range of flow you're trying to measure, say 10 to 15,000 pounds an hour of steam, depending on the line size, a vortex meter would be a perfect application for that. So vortex meters can be used in liquid, gas, or steam applications. On the liquid side, we like to keep the viscosity low, typically below 2 or 3 centipoise. That's not to say we can't use a higher viscosity. We have a sizing program that we would throw the numbers in and take a look at it. So if you do have a high viscosity application, let us know, and we'll take a look at the application by throwing the numbers in our sizing program and let you know if it'll work. Any fluids that are compatible with stainless steel and Hastelloy C, high temperature applications up to 842 Fahrenheit. And typically we like to avoid slurries and extremely high viscosity applications. But again, slurries we stay away from. The high viscosities, let us know, and we'll run the program and give it a yay or a nay. Gas applications, a very easy application for a vortex meter. We do a lot of natural gas, nitrogen, air, hydrogen applications, as long as the pressure is typically above 100 psi to increase the density. That's another basic application for a vortex, and as long as those materials and gases are compatible with stainless and Hastelloy. Steam is probably the most applied application for a vortex. I would say in the solid, 50% of vortex meters are sold in steam applications. Just a great meter for steam. We have a built-in temperature element, so for saturated steam, we can get a true mass flow measurement. Superheated steam, we can use the temperature element and the measured flow rate and a program pressure, and we can also get a mass flow as well for steam. Vortex meters are available in 1/2 inch through 16-inch line sizes. Flange ratings, standard up to about 900 ANSI, and we can do 15 and 2500 upon request as well.
Here's an example of a high temperature steam, high process temperatures up to like 450 C. It's an ideal technology for superheated and saturated steam like Paul mentioned. Also, you can do cryogenic applications because we can go to temperatures as low as a minus 196 C for applications such as liquid oxygen or maybe even LNG natural gas. This photo shows an extended neck version used to remove the electronics from the effects of the extreme process temperatures. The converter or transmitter can be a local display or it can be remote mounted. Steam injection is an increasingly common method of extracting heavy crudes from formations, and it's known as enhanced oil recovery. And it's the main type of thermal stimulation that is used in oil reservoirs. This diagram depicts the steam flood method, sometimes known as a steam drive. Some of the wells are used to inject the steam, and other wells are used for the oil production. And what it's doing is there's two mechanisms that drive the oil. The first is to heat the oil to higher temperatures to decrease the viscosity so that the oil more easily flows through the formation toward the producing well. The second mechanism that's going on here is the physical displacement employed in this manner, similar to water flood, in which the oil is physically pushed to the production well. And we see a lot of steam applications in this type in the energy industry.
Next, we're going to discuss the Coriolis flow meter. So Coriolis is a true mass flow measurement. The previous two technologies, the vortex and magnetic flow meters, are considered or volumetric type flow measurement. And the Coriolis that we're discussing now, that is a true mass flow. So if we look at the example on the left, mass is mass. The mass of a liquid never changes. So in the example on the left, we have a beaker filled with say, water at about 40 degrees Fahrenheit, and the mass is 1,000 grams. The density at that temperature is 1 gram per cc, and if we do the math, that gives us a volume of 1,000 cc's of volume of water. In the example on the right, the temperature goes up to about 100 degrees Fahrenheit, but the mass stays the same at 1,000 grams. The density, because the temperature increased, the density is going to decrease down to 0.99225. And so if we do the math and divide the density into the mass, that gives us a volume of 1,007.8 cc's. So as you can see, as temperature changes, the density changes, and that in turn changes the volume. But the mass never changes. So using a Coriolis to measure flow is an extremely accurate way, and let's talk about that here. So in the illustration at the top of how the Coriolis works, we're looking at the Coriolis force, the Coriolis effect. In the illustration on the top, you can see there's an inlet pickup and an outlet pickup. If we took this meter and we filled it with liquid and clamped it off, the two pickups, the signal will be in phase with one another. So there's nothing going through the meter. But once we open up those valves and flow starts to go through those tubes, the Coriolis effect or Coriolis force takes place, and you have a phase shift between your inlet pickup and your outlet pickup. So this phase shift is proportional to your mass flow. With a Coriolis meter, we can also get a second independent variable, and that's density. So we said that these tubes are measuring the twist. Well, they're also resonating at a known frequency. And when there's a change in frequency based on the density of the process, that frequency is proportional to the density. So we can get two primary measurements in mass flow and density out of a Coriolis. But we can actually get a little bit more because we're doing a temperature compensation of the tubes. So that also gives us a very good temperature measurement as well as of the process. So we can get mass flow, density, temperature. And if you're doing a concentration measurement, say like a alcohol, water, or bricks measurement, we can get a concentration measurement out of the Coriolis as well. So the minimal, or I should say no moving parts, really no maintenance with a Coriolis. And a Coriolis gives you so many diagnostics from drive gain circuit, signal circuit, many advanced diagnostics, and health checks, tube health checks. So it really gives you a window into your process as to what's going on. So Coriolis meters can be used in liquids or gas applications, perfect for slurry applications, high temperature up to about 665 degrees Fahrenheit, cryogenic applications, can use at high viscosities. Turn down is very large, so you can go almost down to zero flow. And one of the big advantages of a Coriolis meter, which we'll see later on, is that there's no flow conditioning required. With some technologies, you need a lot of upstream and downstream piping requirements, but with a Coriolis, you really don't need any. We can measure multiple phase fluids in the same pipe. So in the upstream oil and gas industry, we can do a water cut and a gas void fraction measurement in this one device. We can do, when we say multiple phases, the concentration. So we're mixing, say, a water and a glycol, which are two different densities. So that's considered like a multi-phase. So it's a very versatile meter for a lot of applications. Meter sizes available from a fractional 0.1 inch all the way up to 12-inch inline size.
This is a lease allocation application. What you're looking at there, it's a separator where well production is separating the gas from the liquid, and then also water. Coriolis technology, like Paul mentioned, it's the only technology where the flow meter can yield continuous water cut measurement as well as the gas void fraction. In addition to the process variables Paul mentioned, mass, volume, density, temperature, with the right math equations in there, you can also get total net oil values, API barrels corrected 60 degrees F, water cut values, gas void fraction value, total gross volume of oil, and total mass of oil. And I know we're talking about flow meters here, but of note is that the density accuracies on the Coriolis technology are so good, actually down to 0.0005 grams per cubic centimeter. The Coriolis meter is often applied as a density analyzer.
Okay, so next we're going to talk about the variable area meters, also known as rotometers. How the variable area meter works is that you have a tube, and then you have a float within that tube. And as the force of the liquid pushes that float up, based on the known geometry of the tube, we can calculate what the volume is going through that tube. So there's two types of rotometers. You have metal type and glass or plastic type variable area meters. And in the metal type, you have that float, and it's magnetically coupled to a pointer. And as the flow pushes that float up, it's magnetically coupled to the pointer, so that pointer will point to the scale as an indication as to how much flow you have going through the meter. On the glass and plastic type devices, that scale is imprinted on the tube itself. So you would use the top of the float and see where that lines up and on your scale, and that would determine, then you can read how much flow is going through there. So variable area meters, down and dirty, basic units. There's no external power needed, but you could, if you like. They are available with a 4 to 20 output and HART protocol as well. They're ideal for gas, steam, or liquid applications. Again, any type of flow application we can use the variable area meters. They're easy to install with low maintenance. The only thing on the installation side, it's not a bad thing, but flow must be going in the up direction. You have to have that float being able to move up and down. They're very durable, and they're very easy to install with minimal pressure drop.
Here what you're looking at is some sampling systems that are often used for analytical purposes. So a sample stream is pulled off of a process, and they run through a rotometer to control the flow. And one of the reasons the rotometer works well is because the gas flows are typically very low, and the rotometer allows for very precise measurement and control of the gas flow. So it's perfect for these type applications. Here we're looking at the ultrasonic flow meter technology. This is a picture of a clamp-on. In ultrasonic flow, there are two common types of techniques used, transit time and Doppler. The most common, and what's depicted here, is the transit time technique. And the ultrasonic flow meter measures the difference in time between the upstream signal and the downstream signal. Ultrasound is a mechanical wave, so it's influenced by the flow of the process medium. So what happens is travel time from transducer 1 to transducer 2 in zero flow is the same. As soon as flow is induced, that flow affects the speed. It decelerates the transit time when it's going against the flow, and it increases the transit time when it's going with the flow. So if you just subtract those differences, you actually get a direct velocity measurement. So flow meters are used to measure the velocity of liquids, and it can be used in really extreme applications. Simple water, molten sulfur, chemicals, hot resid flows in the refining industry. Their accuracy is good enough to be used for custody transfer of both gases and liquids. What's nice about one of the advantages in the growth of the industry for ultrasonics is it's pretty much independent of line size. So you can measure very large lines with no pressure drop. You can do it at a reasonable price where, for example, a flow meter on a 72-inch water flow or gas flow, that meter would be much more expensive typically in other technologies and maybe not even doable. Here's a picture of wetted ultrasonic transducers on flare gas applications. Flare gases are kind of a perfect world for an ultrasonic meter because varying composition in a flare application really doesn't matter to the flare meter. With some very few exceptions, the composition can change and you can still maintain the accuracy. Here you're looking at clamp-on application, and this is specifically a high temperature. You go up to 1200 degrees F in measure. So clamp-on measurement can be very useful for flow surveys and temporary measurements, but of note is that clamp-on tends to not be as reliable as a wetted type installation like we saw in the flare gas application.
Okay, next we're going to talk about the DP flow measurement. In the differential pressure flow measurement, you have a lot of different types of primary elements. You have orifice plates, pitot tubes, venturis, V-cones, accellibars. So you have a wide variety of what we call a primary element. And with this primary element, the purpose of it is to create that differential pressure. So again, the orifice plate in this example is our primary element. And when that's put in the line, it's connected to what we call a secondary element, which is a pressure transmitter, a differential pressure transmitter. And the pressure transmitter is reading that differential pressure between upstream of the orifice plate and downstream of the orifice plate. And by utilizing Bernoulli's principle, we can then calculate what the flow is going through that orifice plate. DP measurement is, probably one of the oldest technologies to determine how to measure flow. In today's market, it still makes up probably 50% of all flow measurements, utilizing some type of primary element with a differential pressure transmitter. In most cases, it's less expensive compared to other technologies. The installation doesn't really matter, the orientation, horizontal, vertical, flow going up. So it's easy to install. It can be used for pretty much any type of gas or liquid applications. You just have to make sure your primary element metals meet up with your application, your process. And the maintenance is similar to a pressure transmitter where you may need to zero the transmitter or drain the vent or vent out some gas. So it's very, very simple type of measurement. In this example, we have an accellibur, and this is a natural gas application. And the reason why we went with an accellibur in this type of application, because we had minimal upstream and downstream piping to install the device. So this was the best suited type of device for the application. because as you can see, again, there's no flows going from left to right, and there's no downstream piping after the elbow, and you can't see it in the picture, but there was none downstream either. So this was the best meter for the application. So now that we've gone through all the different technologies, which one do I choose? There's a lot to consider. And some of the questions that we have to ask the customers is, well, what are the process conditions? Is it a liquid, a gas, or a steam application? Because if it's a gas application, well, we're not going to think of a magnetic flow meter. If it's a steam application, we're not going to use a mag meter. If it's a liquid with 3,000 to 5,000 centipoise, then that probably eliminates a vortex meter. So just knowing what type of process, liquid, gas, or steam, that could gear us in which direction we want to choose. So then we're going to ask more questions. What are your flow rates? What's the pressure? What's the temperature? If it's a high pressure application, 1,500 pound ANSI flanges, we may look at a vortex or a Coriolis. If it's a cryogenic application, again, a vortex or a Coriolis. If you want a density measurement out of the device, then we're going to lean towards a Coriolis meter. If the viscosity is too high, then again, we may shy away from the vortex meter. So all these questions come into play when we're selecting or recommending what the flow technology is best suited for your application. Volumetric or mass flow. We said the Coriolis is a mass flow device, and the others we mentioned are volumetric. Line size may come into play. Like Craig said, if you have a 72-inch line, then a clamp-on ultrasonic may be best suited and most economical for that application. Excuse me, the flange rating. This one gets a little tricky sometimes because a lot of times we assume that your application is 70 degrees and 100 psi, and that falls in the range of 150-pound flange. But your system, the overall rating of your system is a 300-pound flange. So we can't always assume that just because your process conditions are, say, lower in this example, that we can just go with a 150-pound flange. So it's common we're going to ask you what your flange rating you require, because that's going to mate up to what your system is rated at. And then the accuracy is always important. Sometimes accuracy is important, sometimes it's not. If accuracy is critical, then Coriolis is going to be the best solution there. Pressure drop's always a concern, because that means more energy consumption on the end user side. So having the least amount of pressure drop is typically the most important. With that goes hand in hand the accuracy. Sometimes the greater the pressure drop, the more accurate the device is going to be, and the less pressure drop could mean a lesser accurate device. And then the elephant in the room is always, how much do you want to spend? And we all want to spend as little as we can and get the most bang for our buck. But sometimes it's just not in the budget to spend what a Coriolis may cost on getting a mass flow, a density measurement, and everything else. And sometimes your budget is $500 to $1,000, and a rotometer, variable area meter, may fit in perfectly for that application. Turn down, each meter has its own range of turn down, so the greater the turn down may lead us to one technology or another. Installation considerations, like the Acelabar, we had no upstream and downstream piping. We could have used a vortex in that application or some other technology. There wasn't room on the footprint side for a Coriolis, so the Acelabar was just the best way to go for that application. Material considerations, like we said on the mag meter, we have all the materials. We don't have all that material on a vortex meter, say. So again, these are all questions that we're going to ask to narrow down what is the best meter for your application. And then general purpose and explosion proof. That kind of goes down the middle, depends on the installation, depends on the plant. Chemical refineries are typically more on the explosion proof side. Other facilities, the general purpose type is acceptable. So here's a little flow selection guide that we put together. And let's let's pick one here. Let's look at the viscosity, high viscosity. So the third one down is high viscosity, and you can see a magnetic flow meter is good, Coriolis is good, ultrasonic is good. Probably want to stay away from the vortex meter in those cases, and the variable area meter as well. DP flow is 50-50 on that one, but it's not going to be our first look for a high viscosity application. A couple down from that, the solid content. Again, a mag meter is good for that. So it really depends on what the application is as to what meter we're going to look at. Here's some typical upstream and downstream considerations. Usually someone asks what the upstream and downstream requirement is. The typical rule of thumb is 10 and 5. 10 diameters up and 5 down. And what we mean by diameter is if you have a 4-inch pipe, and we say we need 10D, so that would be 10 times 4, so that would be 40 inches upstream, and 5D downstream would be 20 inches downstream. Now, these illustrations here are actually for a magnetic flow meter. So you can see in the illustration on the bottom left-hand corner where it has a reducer, that's a concentric type reducer, and with a mag meter, you can use a concentric reducer right into the meter and go back up on the outlet of the meter. So say you have a 6-inch, go down to a 4-inch meter, and then back up to a 6-inch line. So you need no upstream and downstream pipe requirements. But every technology is going to be a little bit different. Coriolis is very forgiving. You really don't need any flow conditioning. Vortex, you're going to be in the 5 to 10 and maybe even 20 pipe diameters if you have a control valve. You have to look at each installation differently and see not just what's upstream immediately, but your entire system to kind of get a good feel to see how much upstream piping you require. And here's a Coriolis installation, and really for pretty much all flow meters, the ideal installation is with flow going in the up direction. But that's not always the case. There's tons and tons of installations where it's horizontal, and that's okay. The thing about the horizontal installations, you just want to make sure that whatever is upstream and downstream of the meter, you want to make sure the line is full at all times. Is there a valve downstream of the meter creating some form of back pressure? The key is to make sure the meter is full at all time. And that's why we say it's ideal to go in a vertical up, because in that case, the liquid is always, or gas for that matter, it's always going to ensure a full pipe. And these installations for Coriolis in the horizontal installation, if it's a liquid, we want the tubes down, so that way we can ensure they're always full. If it's a gas application, we want to ensure that the tubes are up, because that way if you have any droplets of liquid, any condensate going through there, that's going to fall out of the tubes and it won't disrupt your measurement. There's one thing to point out with a Coriolis meter, you really never want to install a meter on its side, because a Coriolis uses two tubes and the flow is going through both of them. So if you install that meter on its side, and say it's a gas application and you have some droplets of water going through, those droplets of water will go through the bottom tube versus the top, and that will really mess up your measurement. So it's never recommended to put a Coriolis meter on the side. And that's about all I have on the presentation side, and we'll open it up for questions.
Yeah, Paul, we got several questions. I'll go ahead and start asking some of these. For reduced bore vortex design, this design, the pipe size changed just before the sensor shutter. So does the upstream and downstream link need to change also?
So with the reduced bore, we look at, in the instruction manual that gives requirements, we would look at it just like a standard meter. So if you're coming off of an elbow and you have a single plane 90-degree elbow, we would still need, say, 10 pipe diameters after that elbow before we go into the reduced bore. The reduced bore design is basically has concentric reducers built into it, so it is conditioning the flow going into the meter where the shutter bar sensor is, but we still have to take into consideration what's upstream of the meter and make sure we have sufficient straight pipe so we have a clean profile going into the meter.
Next question on mag meters. In the past, iron correction was a factor. I don't think this is the case anymore, is it?
Iron correction. I'm not sure what you mean by that.
Yeah, I'm not sure either.
Yeah, let's get who sent that in, and we'll get back to them on that one.
Okay, sounds good. On viscous fluid, so 10K to 20K centipoise, in which the precipitation can plug or occur, do you recommend any other flow technologies beside mag meters? And also, do you have to balance the accuracy and pressure drop?
So on the viscosity side, yeah, that's a pretty high viscosity. A mag is a straight through device, so typically, not to say it can't plug, but we have to look at what the pressure is and making sure there's enough push to get that through. The one thing that occurs in a mag meter with that high of a viscosity is that you have more movement in the center of the tube versus on the walls. So that's a pretty high viscosity for a mag meter. A Coriolis works pretty well in high viscosity applications. We've had applications, basically toothpaste and peanut butter, pushing it through a Coriolis. So that's something, let's get back with that customer and we can discuss the application.
Next one, on a vortex meter, the only volumetric flow rate for liquids, can this be outputted in barrels per day?
Yes. Yeah, there's in the vortex is programmable, so you can set it up in, there's a lot of different engineering units, and I know barrels is one of them. So yeah, you can set up your engineering unit in barrels per day.
This is a two-part question. Any experience for vortex on CO2 flood in oil and gas, and any experience on mags on water flood in oil and gas?
We'll have to get back to him on that one. We'd have to look at the process conditions. I personally don't have experience with that, but let's look at the application and see what we can do.
I could input a little bit. I have had experience with CO2 floods. You got to, like Paul said, look at the application. My experience has been the CO2 has been very high pressure. Technologies that I have seen used are DP and ultrasonic.
Next question. Is there a way to take a volumetric flow meter and get get mass flow? If so, how?
Yeah. So if you're using, say, a vortex meter, if you're measuring in say gallons per minute, and you have a density measurement, and your density is in say pounds per gallon. So you just do the math. Basically, you multiply your gallons per minute by your pounds per gallon density, and gallons cancel out, and you're left with a pounds per minute value. So that's with a vortex meter, it's a volumetric device. In a Coriolis meter, we get a lot of requests, even though it's a mass flow device, we get a lot of requests to measure in volume. And that's what the Coriolis is doing. It's measuring both the mass flow and the density, and then doing the math to give you a volumetric flow rate.
And I would add on to what Paul said there. So what I would ask a user is, how important is that measurement? Because now you're talking about an inferred measurement versus a direct measurement. Like Paul mentions, the Coriolis meter is a direct measurement of density. And my experience also has been process fluids. The densities they tend to not be very tightly controlled. So if the density measurement was very important to me, or the mass measurement was very important to me, I would shy away from an inferred measurement and go with a direct measurement like a Coriolis meter. Depends on how important that measurement value is.
Okay. Next question. I'm being told that back pressure control valve can help with entrained gas bubbles for Coriolis meter. Can you explain the theory behind this?
Yeah, if you have too much of a differential pressure, yeah, you can get you get that possibility of creating bubbles, just entrained gas. So yeah, what that back pressure is doing is just, in a sense, keeping the pressure a little more stable at the device, so you don't have that big pressure drop, and it's you're not creating that entrained gas.
So I
Great.
would add a little bit to that, Paul, too. So it sounds like what they're describing is actually a cavitation phenomena. What you can actually, what they're doing is the correct thing to do. What's interesting is you can take, we've had situations where we've used ultrasonic because ultrasonic will detect cavitation, and you can actually tune your valve to this is how far open it should be maximum to keep cavitation from going on. Reducing cavitation is good for the whole system, not just the flow meter.
Okay, next question. I think I can answer this one. Can I get a copy of this presentation? Yes, we'll get you that. Can you share the selection guide? Also, do you have a table that shows the advantages and disadvantages of each type, accuracy and cost, etc.? This would be nice for young engineers on my team. Yes, we're actually working on that now and hope to get that out soon. Next question, what is the best for steam applications where a 20-to-1 turndown ratio is desired?
My initial answer is going to be a vortex meter. That's, vortex meters have very high turndown. If you look at the, turndown is always a tricky term because as a manufacturer, we say the turndown is the meter's maximum flow to the minimum flow. So if we throw the numbers in our sizing program, some applications, especially steam, it's going to be as high as a 30-to-1 turndown. But that doesn't necessarily mean it's a 30-to-1 turndown for the customer's application. If our maximum flow is 100,000 and we can, go down to a couple thousand, but their application is from 20,000 and they want to go 20-to-1 turndown as well. So that the minimum flows are going to conflict with each other. So where the reduced bore does come in, depending on the line size. So yeah, to me, if you say you want 20-to-1 turndown in a steam application, a vortex is going to be my first thought.
Next question, what are the pipe up and down stream requirements for a Yokogawa Coriolis meter?
There actually is no requirements for the Coriolis.
Next question, any advice? What is the best recommended flow meter for two-phase flow, which is challenging?
Yeah, that's something we'll have to discuss. A Coriolis is probably going to be the best suited. A vortex won't work well. Same with a mag, and it depends on what that two-phase is. If you're talking a liquid and a gas, why a mag wouldn't work is because a mag meter is calculating. We said the voltage potential, but it's calculating based on the area of the flow tube. So if you have gas bubbles, that's taking up volume in there. The meter doesn't know that, so it's still going to calculate a flow based on a full pipe. So, mag is definitely out, but a Coriolis would, I would say, yeah, Coriolis is best suited, but it's definitely, anytime you have a two-phase flow, it's more than a discussion like this. We really have to get the conditions and go through that. So make sure you find out who asked that question and we'll get in touch with them.
Okay, a couple more questions. I typically don't recommend mags for low conductivity applications for obvious reasons. However, the AdMag CA claims to read down to 0.01 microsiemens. Have you any experience with this mag in ultra low conductivity environment?
Yeah, we use the CA in DI water applications all the time. It is a great meter, and I apologize I didn't mention that earlier, but yeah, standard mags go down to about 1 microsiemen of conductivity, and the CA is 0.01. So yeah, we have a lot of applications in DI water, low conductivity applications. I would stay away. We've been asked if we can do hydrocarbon type applications with the CA. And hydrocarbons just aren't conductive, and even if they have some water mixed in, if it's not a perfect homogeneous mixture, in which it's typically not, a CA is just not going to work. But if you have DI or any chemical that's very low conductivity, we can do it.
And we got time for one more question. What is the max viscosity Yokogawa recommends for its Coriolis meter?
I really don't think we have a max number on there. Like I said, I know we've done peanut butter and toothpaste applications. We've done cookie dough applications, and off the top of my head, I just don't know what the viscosity was of those of that process. I can find out, but I don't think we put a limitation as far as the high viscosity side. Our sizing program may have some caps, but that's kind of more so based on pressure drops going through the unit and accuracy. But as far as the number itself, I guess let me look and see if we have a maximum cap number on that one.
All right. Well, it is noon. I think we got to most of the questions. If we didn't answer your question online, we can answer it, send it to you directly. Guys, thank you for a great presentation. I'm going to turn it back over to Bill to close us out.
Yeah, thank you for the great content, everybody. And thank you to everybody who put in questions.